Welcome to another deep dive, everybody. And today we're going to be talking about something that's pretty hard to get your hands on.
Literally.
That's right. Seaborgium.
Yeah.
An element so elusive it would make a chameleon look easy to spot.
Right.
We're using excerpts from history and the Seaborgium Wikipedia page to sort of uncover its discovery and all those little things that make Seaborgium really special.
Yeah, and I think it's really interesting that the story of Seaborgium actually starts a lot earlier than you might think. We're talking late 19th century.
Oh, wow. Okay.
Yeah, with Dmitri Mendeleev.
Mendeleev, the
Yeah.
periodic table guy,
Seems
right?
like, yeah.
I mean, that's a name from science class that you kind of never forget. But what's he got to do with Seaborgium?
Well, his periodic table was more than just a way to, organize the elements.
Right?
It was like a roadmap to future discoveries.
Mm.
He was able to predict elements that hadn't even been discovered yet.
Oh, wow.
And he did this based on the patterns he saw on the table. And one of those predictions was for an element called ecotungsten. And guess what?
What?
That turned out to be Seaborgium.
So he basically called it like over a century before anyone even knew it was a thing.
Basically, yeah.
That's incredible. I mean, was he right about other elements too?
Yeah. Oh, yeah.
Okay.
Many of his predictions turned out to be accurate.
Wow. So it really shows you the power of the periodic table.
Yeah.
It's like not just for organizing things, but like actually understanding the basic building block.
Yeah,
That
fundamentals.
makes you think, like, what else is out there?
Right. Exactly.
Still waiting to be discovered.
Right.
But okay, so Mendeleev kind of set the stage. How do we actually discover Seaborgium? Like, who gets the credit?
Well, fast forward to 1974. And it's a race.
Ooh.
Two teams, one in America and one in Russia, both trying to be the first to create Seaborgium. Imagine the excitement.
It's a scientific showdown. I'm all ears. Tell me about it. Like, what were they doing? Like, what approaches did they take?
All right, so the American team, led by Albert Chiorso and E. Kenneth Hewlett, they bombarded californium-249 with oxygen-18 ions. Think about trying to merge two teeny tiny atoms going incredibly fast, hoping they fuse together.
Oh, wow.
Yeah, and they actually succeeded. They created Seaborgium 263 meters, which has a half-life of just 0.9 seconds.
0.9 seconds. That's like barely any time at all. How could they even know they made it?
Well, they had super sensitive equipment, incredible detection methods.
Yeah, I guess you'd have to.
Oh, yeah. And get this, while the American team was celebrating, the Russian team led by Georgy Flerov and Yuri Oganeshin, they took a different route.
Okay.
They bombarded lead with chromium ions. It's called cold fusion.
Mm-hmm.
It's like coming at the atoms from the side,
Oh, okay.
to make that fusion release. And they created Seaborgium 260. And that had a half-life measured in milliseconds.
Milliseconds.
Right.
That's like trying to read a message, before the ink disappears. Like, poof, it's gone. Okay. So we've got two teams, two different isotopes, super short half-lives. Talk about a photo finish.
Yeah.
What happens next? Who gets to name it?
This is where it gets interesting. It's not every day you get to name an element.
Right.
And it's really rare to name one after someone who's still alive.
Oh.
So both teams, initially they had more, I guess you'd say, traditional names
Okay.
based on the atomic number. But then the American team, they went for a bold move. Seaborgium,
Oh.
to honor Glenn T. Seaborg, a living legend.
Wait, a living person? I feel like that's going to cause some drama in the science world.
You're right. IUPAC, that's the International Union of Pure and Applied Chemistry, they're the ones who make the rules about these things. And they initially pushed back against the name,
Okay.
but the scientific community, they were having none of it. They got behind the Americans. Think petitions, letters, arguments at big conferences. It was intense.
So they really fought for it.
They did. And you know what? In a rare moment of bending the rules, IUPAC accepted Seaborgium in 1997, one of very few elements named after a living person.
Wow.
And the best part, Seaborg got to see it. He even joked about the day chemists would talk about, things like sodium Seaborgate.
Okay, that's pretty cool. You get an element named after you, and you're still cracking jokes about it. But we know it exists, but what do we actually know about it? I mean, how do you study something that only lasts for like a blink of an eye?
It's a challenge. Studying these super heavy elements like Seaborgium, it's like trying to read a message that's written in disappearing ink.
Yeah. Yeah.
And just to make them, scientists have to use these crazy, powerful particle accelerators, smashing atoms together at these incredible speeds.
Oh,
Yeah.
mind-boggling.
That sounds like a a microscopic demolition derby.
Yeah, exactly. And then on top of that, you got to have these super sensitive detectors to catch, the tiniest little trace of these elements
Yeah.
before they just poof,
Yeah, they're gone.
decay away. So it's a challenge, I get it. But what if we learned about it, despite all of that?
Well, even with all that, even though it's like trying to catch a lightning bolt in a bottle, we've learned some interesting stuff.
Okay.
Like, we know that it's probably this super dense solid metal,
Okay.
and we're talking way denser than anyone thought.
Wow.
Like, some calculations put it between 23 and 35 grams per cubic centimeter.
23 to 35 grams. Wow. Okay, so for everyone listening, imagine a chunk of Seaborgium the size of, say, a golf ball.
Yeah.
That would be, that'd be heavy. Definitely wouldn't want to drop that on your hood.
No, you would not.
Okay, so dense, heavy. What about how it reacts with other stuff? Like, what do we know about its chemical behavior?
Well, we think it probably behaves kind of like its lighter siblings in group 6
Okay.
on the periodic table.
Hmm.
So elements like molybdenum and tungsten.
Ah, so it's following the family trends, so to speak.
Okay.
Okay, so that means we already know how it's going to behave, right?
Well, not so fast.
Oh.
Those predictions are a good starting point, but there can always be surprises.
Uh-huh.
So, for instance, we think it probably favors a +6 oxidation state.
+6. Remind me what that means again. I took chemistry, but it's been a while.
Sure. So think of it like Seaborgium has 6 hands that it uses to grab onto other elements.
Okay.
And it likes to use all 6 when it's making compounds.
Oh. Okay.
And we've actually seen that.
Yeah.
Scientists have been able to make something called Seaborgium hexacarbonyl. It's this really interesting compound, and it's volatile.
Wait, volatile. Is that like dangerous?
No, not in this context.
Okay.
Volatile in chemistry, it just means something that evaporates easily.
Oh, okay.
Like, think of dry ice.
Yeah.
Turns straight into a gas.
I got it.
And this is actually really helpful because it lets scientists study Seaborgium's chemistry in the gas phase.
So even though we can't really have a beaker full of it and watch it react,
Right.
scientists can still get some clues by looking at these short-lived compounds.
Yeah, exactly. It's like if you want to understand a really shy animal,
Uh-huh.
you can't just, walk right up to it. You got to kind of observe it indirectly,
Yeah.
see its tracks, maybe watch what it eats. It's like detective work, piecing together these little clues about Seaborgium.
That's a really good way to put it. But it sounds so unstable.
Yeah.
What's the point of even studying it? Is there any practical use for an element that disappears so quickly?
That's a good question. And honestly, right now, there aren't any direct applications.
Okay.
You're not going to find it in your smartphone or powering your car anytime soon.
So it's more of a scientific curiosity.
For now, yeah. But it's about something bigger,
Okay.
pushing the limits of our knowledge about matter,
Okay.
making and studying these super heavy elements. It helps us test the periodic table, our models of the atom, and it helps us explore the fundamental forces of the universe.
So it's like a window into the basic building blocks.
Exactly. And who knows what the future holds? Our technology is always getting better.
Yeah, that's true.
We might find new Seaborgium isotopes
Oh,
with longer half-lives.
interesting.
And those could have some really surprising properties. Who Yeah. knows? Maybe even some applications we haven't even thought of yet.
It really makes you wonder what else is out there, What other secrets are hidden in the periodic table? But before we get too lost in the what ifs, let's take a minute to think back on everything we've learned in this deep dive.
It has been quite a journey.
It has.
Starting all the way back in the 1800s with Mendeleev and his prediction of ecotungsten.
Which we now know is
Seaborgium.
Seaborgium. It's
Yeah.
just amazing to think that he saw those patterns and was able to predict
Yeah.
something like that.
It shows you the power of the periodic table for sure.
Definitely. And then we jumped ahead to 1974, the Seaborgium synthesis race.
Oh, yeah.
2 teams going head-to-head, both creating Seaborgium.
Different isotopes, yeah.
Super short half-lives. It must have been a very exciting time for nuclear science.
I can only imagine. It's really inspiring, to see scientists pushing the limits like that.
Yeah. And then, of course, who could forget the naming drama?
Yes, IUPAC bending the rules for, well, a legend.
A living legend at that.
Yeah. It's a nice reminder that science is more than just facts and figures,
Mhm.
There's passion there, there's drama, and, sometimes even a little bit of humor, too.
Absolutely. And then finally, we talked about how challenging it is to actually study an element that disappears so quickly.
It's not easy.
But even with those challenges, scientists have been able to learn a lot about Seaborgium's properties.
Yeah, like that incredible density.
Right, that golf ball-sized chunk that would be impossible to lift.
Yeah, and its chemical behavior, too. Like the fact that we've even seen Seaborgium hexacarbonyl. It's
Yeah.
amazing.
Yeah, all those tiny pieces of the puzzle coming together, right? Even if it is just for a fraction of a second.
Exactly. Which brings us to a final question for you, our listeners. We've talked about how unstable Seaborgium is, how hard it is to make, the fact that it doesn't really have any practical uses right now.
So,
What do you think the future holds for this elusive element?
are there undiscovered isotopes out there? Isotopes with longer half-lives, maybe? And if we find them, what new properties might they reveal? Could they unlock applications that we haven't even dreamt of yet?
These are the kinds of questions that keep scientists going. And while the future of Seaborgium research might be a mystery, one thing is for sure: it will continue to challenge our understanding of the universe and push us to explore the unknown.
That's a great note to end on. I hope you've enjoyed this deep dive into the world of Seaborgium. It just goes to show that even the most fleeting discoveries can leave a lasting impact. Until next time, keep exploring, keep asking questions, and keep diving deep into the wonders of science.